All right, so let's talk about motion. So here's how you can use this video. Throughout the video, there is going to be some green highlighted text. If you're using this to take notes, that's the important stuff that should be in the notebook. There's also going to be blue text throughout. These are questions for you to consider and or questions for you to answer to help you practice the material. Now, throughout this video, there's going to be a visual code that will pop up on the screen and a verbal code that will be said by myself. They can be said in any order, so pay attention. All right, let's get started. So let's start off with this question. How fast are you moving right now? Right, so that's that question, right? How fast are you moving right now? Well, this depends on your frame of reference, right? So when describing motion, right, which is what we're talking about, a frame of reference must be established. So think about it this way, right? So if I'm just sitting here in this room, I would say I'm not moving, right? Because most of the time our frame of reference is established as just the room we're in or like the surface of the earth, right? So, but you could also say, well, the earth is rotating, right? It's rotating about its axis. So where I am, like, yeah, I could be moving like that. Or it's also revolving around the sun, right? We're in orbit around the sun. We're going incredibly fast around the sun. We're also going around the galaxy, right? The Milky Way, right? And our Milky Way, the galaxy is also moving through space, right, compared to different things. So it's important that we establish a frame of reference. Now, for the most part, it's just given, right? Hey, the surface of the Earth, for the most part, for us, is stationary. That's mostly what we use as the frame of reference. Now, where this comes into play here, right? Galileo had this thought experiment, right? The laws of mechanics are the same in uniform motion, assuming absolute time and space. So here would be an example of that, right? He would say like velocities added, right? So if we're looking at a train, right, somebody throws a ball on the train, well, those velocities add. Here's another thing, like he was saying that like, well, as long as you are in constant motion, like the laws of the mechanics, right? Like motion is going to be the same. So, and the example that he uses for like relativity is that if somebody's on a sailboat and they drop their binoculars from the mast, it goes straight down. Okay, but if you're looking from the shore, well, you'll notice that it makes a curved path. And it's like, well, what distance did it travel? Because those are two different distances based on your relativity, right? So this was sort of like an early understanding of like relativity. Now, Einstein came along with special relativity, and he extends this to all physics, including the electromagnetic spectrum. This adds that crucial part of that speed of light has to be constant for all observers. So if we use that example that Galileo used, right? Well, he didn't use it on train, but like if we use that example of like a train, you throw a ball on a train, well, we add those velocities, but would that happen for the speed of light? Well, Einstein was like, well, that can't be possible because the speed of light must be the same for everybody, no matter your frame of reference. So time and space warp to keep the speed of light constant. So this happens at very high velocities, right? We're talking close to the speed of light, like you have time dilation. Time slows down the faster you get to the speed of light. So it's all kind of a complex way of saying this, right? In physics terms, there's no difference between being at rest and moving at a constant velocity. And acceleration is the only real or absolute motion, right? We need to keep that in mind for later chapters, but this is important when we're talking about motion. So let's jump into how we show motion, right? So first we need to talk about rates, right? A rate is a ratio that describes how one quantity changes compared to another, and it's usually compared to time. Not all the time, though, right? So here would be examples, like miles per hour, right? So if you're looking at your speedometer, you see that it's miles per hour. Kids per household, right? So this doesn't compare it to time. This is just saying, like, hey, like the average like is 2.5 kids per household, right? Gallons per minute. If you're measuring like water flow, right? You turn on a sink, right? How many gallons per minute? That's comparing it to a time. Meters per second. Okay, great. Now we've got another like distance per unit time. Calories per serving. So if you look on the back of your nutrition labels, it's like you've got calories per serving, right? How many calories are there in a serving? Beats per minute, so this could be in reference to music, or like if you're checking your pulse, how many beats happen in a minute. These are rates, right? We're including two different units, right? Now, but before we get to like motion, we need to talk about one distinction we need to make, right? Distance versus displacement. Distance is the total path lengths traveled. It's a scalar quantity, meaning it only has magnitude, no direction. It's always going to be positive. Now, displacement is the change in position from start to finish. It is a vector quantity, meaning it has direction. So we need to keep track of positive, negative, or zero, right? So I've seen it written different ways. So if you look up at the top, these little graphics show like distance is just the total distance traveled, and then displacement is the change in position from start to finish. But what we really need to keep track of is whether they're moving left or right, because as we get into more complicated equations, we need to keep track of what direction that object is moving, positive or negative, right? So that's the important thing that we need to establish here, right, is distance versus displacement, the direction that that object is moving, right? So you might see these used interchangeably, like just like speaking, but like there is a distinction here, right? Now, let's answer this question, right? So if we look at a race, like the 100-meter, dash, so like you know who's going to win. It's because they cross the finish line. But let's just say people are not racing side by side or at the same time. How can it be determined who is faster? So you can see here, this was a promo that ran on Shark Week. That they were saying like, hey, Michael Phelps versus a great white shark, who's going to win, right? Well, they obviously couldn't do this, right? A shark doesn't know it's going to be in a race. It could just swim away, right? So there could be some danger established with that, even though sharks don't really attack humans that often. But you really couldn't do this. So how could we establish this, right? Well, we could compare the speed. So speed describes how fast an object is moving and is a rate of distance over time. It is a scalar quantity. Now, the unit depends on the situation, right? So meters per second is what is mostly used in like physics equations, right? But miles per hour could also be used, right? So that would be like, in a car. You could centimeters per second. So if you're measuring the speed of like a wind-up toy, right? How many centimeters per second? Inches per year. So if we're measuring something really slow, like continental drift, how many inches does it travel per year? Like, the continents move at about the rate that your fingernails grow. You would not want to use miles per hour. That would not make sense. Miles per second. This would be something that you would measure that's going really fast, like things moving in space, right? So all speeds are rates, but not all rates are speeds, right? So we're always comparing two things, but speed is always going to be a distance over a time. Now, like moving on, there are two different types of speeds that we need to talk about. It's still speed, right? But average versus instantaneous. So average speed is the rate of the total distance divided by a time interval. You need a measuring stick and a stopwatch to measure this, right? So this is the equation for it, right? It's just a distance divided by the time, right? And I have the triangle there that if you cover up the variable that you're trying to find, well, it'll give you the equation that you need to use. Now, instantaneous speed is the speed at one specific moment in time, one instant in time. For this, you need a speedometer or a radar gun to measure this. So if you look here, you can see here instantaneous speed. Here's this car traveling. Well, the speedometer would read like 0, then speeding up, then slowing down. But the average, well, I would just take whatever the distance was traveled divided by the time. Now, let's get some practice calculating speed, right? So for the following problem, solve for the unknown variables. I'm going to set this up for you. So let's just take a look at these, right? So I'll go ahead and put all these out there, and I just want to show you how to find the equation, right? So I'll leave this up there, and I'm going to just cover up the equation real fast. Toy car travel is 150 centimeters in 6 seconds. At a constant speed, calculate the speed of the toy car in centimeters per second, right? So in this one, what I'm going to do is I look at that triangle, I cover up speed, and I'm left with, well, speed equals distance divided by time, right? So that's how you set that one up, right? And the units would be centimeters per second, right? And it tells you that. Now let's take a look at this next one. A hiker walks at 2 miles per hour and covers 5 miles. Calculate the time spent hiking. So now we're looking for time. So I cover up time, right? Time equals, and I cover up that, and I'm left with distance divided by speed. So that's how I do that. And my unit is going to be time. So if I'm looking at this, it's going to be hours, right? Because I'm measuring miles per hour. Now, the last one I talked about, plate tectonics. Plate tectonics move at about 2.8 inches per year. Calculate how far a plate will move in 500 years. So it's the same principle. I know it seems complicated, but we'll cover up distance, right? We're looking for distance, and it's going to be speed times time. So that's how you find the equation. And how far, like that's going to be distance. That's kind of a tricky one, but that one, the unit is going to be inches. You'll get a number. So that's how you set up these equations. So now let's move on to velocity, right? So velocity is speed with direction. It describes how fast an object's position is changing and which direction it's moving. So it is a vector quantity, and you'll notice, like, look at the examples here, right? And the important thing, especially in physics, and I think people get this confused, like, well, why would we need speed and velocity? Velocity, when we plug it into like equations for acceleration, we need to keep track of what direction that object is traveling, right? Whether it's positive or negative. So yes, you can see, oh, it's 20 miles or 20 meters per second east, right? But the important thing is, well, especially when we're plugging them into calculations, we need to be able to determine what direction it's going, right? So an object can have constant speed, but changing velocity if it's changing directions. And you'll look at here the equation down here. This just means it's change in position over change in time. So if it's moving forward or backward, that could mean that it has a negative velocity, right? And also, this comes into play when we talk about the graphs, a position versus time graph. So at this time, I'll go ahead and give you that verbal code. The verbal code is 634. I say that again, the verbal code is 634. So let's take a look at a position versus time graph, right? So now what we're showing, the time is on the x-axis and position is on the y-axis, where it's located. So this is the important thing, and this is where velocity comes into play. In a position versus time graph, the slope is the velocity, right? The rise over run. So a straight line means constant velocity. A horizontal line means the object is at rest. A curved line means it's accelerating, so the velocity is changing, right? The steeper the line, the faster the object is moving. So if we take a look at some of these examples over here, right? I like this one, it's labeled, but this little graphic here shows you I've got two different cars. So notice, yeah, they're moving in the positive direction, so it's going to be going up. So it's positive velocity. Notice that blue car is traveling slower, so it's less steep, right? It's less steep than that red car. That's catching up that. So that is the slope of the line will be the velocity. And there's a little graph or a little like picture down there that shows, well, constant velocity. You've got positive, negative, or zero. It's that object is at rest. And then you've got slowing down, speeding up. That is acceleration, right? That is acceleration. So let's just get some practice here, right? So if we take a look at this, right? So I'll let you do this one, but I'm going to walk you through this. So here's a position versus time graph that shows the motion of an elevator. So this time we're talking up and down, positive and negative going up, or positive going up, negative going down. Each floor is 10 feet apart. The ground floor is set at 0. So if we take a look here at the different examples, let's take a look at these questions. When is the elevator at rest? Well, this would be a horizontal line. Where are the horizontal lines? When is the elevator moving up? So this is positive direction, right? So this is when it's slanted, going positive, going up and to the right. When is the elevator moving down? Well, it's when the slope is negative, right? So take a look at that when it's negative. Now, these next three questions, they're the same questions. When is the velocity of the elevator 0? That's the slope, right? When is the velocity of the elevator positive? When is the velocity of the elevator negative? These are the same questions as those first three. Now, these next two questions, I want to show you how to calculate this, right? So I asked you, calculate the velocity of the elevator when it is moving up. So in this one, look at the equation for velocity. I've got change in position divided by change in time. You're just finding the slope of that line. So if you find one of the lines that have positive velocity, where it's moving up, and I'll help you out, that's B and D, right? All you have to do is find the slope, right? And those slopes are the same, right? Those slopes are the same for this one, right? Calculate the velocity of the elevator when it's moving down, so you'll have a negative velocity in this one, right? So in this one, well, that's F and H. So just look at those lines, just find the slope. That's it, and that will be the velocity. And you will get a negative velocity because it is moving in the downward direction, right? So let's get some practice with another graph here, right? This one's making the graph. So a student starts 10 meters from a classroom door. The student walks away from the door at a steady pace and reaches 40 meters after 15 seconds. The student then immediately turns around and walks back to the door, reaching 10 meters again at 25 seconds. Graph the position versus time from 0 to 25 seconds. So the first thing to do is just set up the X. So this is a position, right? So I'll just put, this is a position versus time, right? I'll just do that. Now I need to set up the scale. I'm just going to start both of these at 0 for the sake of time. Now my X-axis is the time, so it needs to end at 25 seconds. So I'm going to just go by 5. 5, 10, 15, 20, 25, right? Right, so there's 12 spaces here, right? Now my position, it goes up to 40 meters. So I'm going to do the same thing, right? I'll do 5. Actually, you know what? I'm going to go by 10s here, right? So I'll go, yeah, I guess I'll count by 5s, but I'll make this 10, 20, 30, 40. That should do 10, 20, 30, 40, right? So now I can start to graph this, right? So if I look at this, well, starts 10 meters, right? So they're going to start right here, and they move from the door at a steady pace and reach 40 after 15 seconds. So that would be 5, 10, 15, and they reach 40. So that's going to be, oh, I can move that. Oh, let's see. Am I going to, all right, there we go, right? So that's going to be here after 5, 10, 15, and I reach here, right? So it's going to look like this, right? That's supposed to be straight, right? Then immediately turns around and walks back to the door, right? So I'll let you finish this one because this is good practice for making those graphs, right? But that's just how you do that, right? You're just basically graphing what it says on the, let me just clear all of it. There we go. Perfect. All right, go back to cursor. All right, so last thing we need to talk about is momentum. So this is just sort of a little addition on to what we've been learning here. Now, momentum is the product of an object's mass and velocity. It represents its inertia in motion. It's the property of an object to keep moving, right? Now, it is a vector quantity because velocity has direction, right? So that's the equation, right? Mass times velocity. You can see those arrows mean that they're vector quantities, and it has, well, an equation that you can use as well, right? But the unit is just you multiply, kilogram meters per second, right? You just multiply the unit, mass times the velocity here, right? Now, here's why this is important, right? And what we've been learning about speed, when we're looking at like one object moving, this is great when we're talking about objects colliding with each other because momentum is conserved and can be transferred during a collision. So that just takes like motion. This is sort of just a little introductory to the next step when we're talking about momentum. But you can see here, like when bowling, like, yeah, that bowling ball is transferring that momentum into like those bowling pins, right? It's conserved. It's the same amount of momentum. I like to think of it as money in this room, right? So money can change hands, but at the end of the day, it's the same amount of money in this room. It's just in different places, right? Once again, like there is too much unknown in the universe to take a break from learning. Get out there and question everything.